one of the things I said about domain and range is that if we know what the picture looks like, it's very easy then to just read off the picture what the domain and range is. That's just one reason why it's good to know what a sketch of a graph looks like. Later on, when we start looking at integration and things like this, to have a rough idea of what the curve looks like is going to be of a benefit. So, sketching graphs, some ideas of how to remember to do these things and so on. Now, some basics. Remember, your axes, they should be evenly spaced. We don't change the scale. That doesn't mean the scale has to be the same on the y-axis as the x-axis. Sometimes that would be impractical. For instance, I don't know, say you had a y value of 100 and an x value of 1. I mean, it's not going to be practical to have the same scale on both. The only time, I guess, where it's vital to have the same scale would be what situation, do you reckon? Yeah, if you're drawing a circle, it's probably a good idea to have the same scale. Otherwise, it'll look like an ellipse rather than a circle if you draw it. Y-intercept occurs when x equals 0, so it's always very easy to find. You can just substitute in 0 and you've got your y-intercept. X-intercepts, well, they occur when y equals 0, so if we can solve the equation, they're going to be easy to find. So if they are easy to find, I'll label in x-intercepts. If it looks like it's going to be too hard to solve the equation, I'm probably not going to worry about it. I might estimate. Okay. So once you've got your intercepts, if you know the basic shape, is it a parabola? Is it a circle? What sort of shape? Then it's going to be easy to draw. Okay? And never ever forget the most basic idea when you first started drawing things, a table of values. I mean, if you're unsure what the thing's going to look like, plot some points. And then you might get a feel for what the curve's doing. Okay, the basic curves. Straight line, I guess, is the most basic curve that we see, and the most basic straight line would probably be y equals x. You've done plenty of work over the years on straight lines, but of course we know every straight line can be written in the form y equals mx plus b. This is how we recognise it. If we saw an equation, y equals 5x plus 2, and for some insane reason we don't realise, oh, that's a straight line, what are we looking for? Oh, well, y is to the power of 1 and x is to the power of 1. Oh, if I see that, I know, okay, it's what we call a linear function, so we know it's a straight line. We will do a lot more work on lines later, of course, but do you remember when we're in the form y equals mx plus b, b, of course, is the y-intercept, m tells us, yeah, the gradient or the slope of the line. So, okay, parabola is a quadratic. All quadratics will be parabolas when we draw them. And so if we see an equation, this time the powers we're looking for, usually y will be to the power of 1, and the highest power of x is the power of 2. Okay, we know we've got a parabola. If it was the other way around, the y was to the power of 2 and x was to the power of 1, still a parabola, but it'll be on its side rather than the other way around. X-intercepts, well, this one is very easy, of course, it's just 0. But for any quadratic, we just solve it. And we know how to solve quadratics. So we should be able to find x-intercepts for any quadratic. The vertex will always be halfway between the intercepts. So once you know the x-intercepts, you can just average those out. You know the vertex is going to be halfway. So let's just do a quick example of a parabola. Y equals x squared minus 4x plus 3. We're going to find the x-intercepts. So we'll solve it. There's lots of different ways I could solve this. If I do it by completing the square, it actually gives me some more information straight away. If I complete the square on this, and I say, well, x minus half the coefficient of x is x minus 2. X minus 2 all squared. If I was to expand that out, I would get not 3, but I would get 4. So to balance it out, minus 1. That straight away tells me that the vertex is at 2, 1. Sorry, 2 minus 1. Remember that idea about shifting curves? And we will look at this idea again, so don't panic if it's like, oh, no. Right? When you group things together, it tells you about how the basic curve is shifted. When it's grouped with the x, it tells me how is it shifted horizontally. When it's grouped with the y, It's not obvious this is grouped with a y, but of course I could move that minus 1 over. That tells me how it's shifted vertically. So I can look at that and say, oh, the vertex is going to be 2, negative 1. Because I've shifted 2. How do I know which way? Well, I look inside and say, well, what would make that equal to 0? Oh, x equals 2 would make that equal 0. So I've moved it across 2 and then down 1. Okay, so there's our vertex. X-intercepts, now that I've already completed the square, I could just solve it using completing the square. X minus 2 all squared is 1. So x is 2 plus or minus 1. We end up with 1 or 3. Okay, let's plot those in. 1, minus 2, 3, bingo. And there's a rough parabola. I didn't bother working out why. Y, of course, would be positive 3, wouldn't it? Because of the y-intercept. Okay, let's keep going up the scale with our polynomials. Linear function, quadratic function. Next one is, of course, the cubic. That's a very dodgy looking cubic. There's our basic one, y equals x cubed. There's a general one, ax cubed plus bx squared plus cx plus d. Again, it's the highest power you're looking for. One of them's 1, one of them's 3. You know the basic shape is indeed a cubic. Not all cubics look like this. Only cubics that factorise to be a perfect cube will look like this. Okay? So it can be a perfect cube, maybe times some multiple, look like that. Otherwise, it'll look something like this. It'll have that up and down sort of shape. That's the other type of cubic you might see from time to time. All right, higher powers. Let's keep going up with the polynomials. Basically, the basic curve, Basically, even powers will all have a U shape, like the parabola. Only x squared is called the parabola. The others still have a U shape. They're not parabolas, they have a U shape. And what happens, as the powers get bigger, the curve gets flatter at the base, which I've tried to exaggerate here, flatter at the base, steeper at the sides. Okay? Same thing happens with odd powers. They will all have that funny, twisty sort of shape. The correct name is inflecting. But again, as the powers get higher, flatter at the base, steeper at the sides. Okay, so there's polynomials. Hyperbolas. The most common one we see is one that looks like that, y equals 1 on x. Could be rewritten to be xy equals 1, of course. How do we recognise it? Well, if I see a pronumeral in the denominator of a fraction, then I've probably got a hyperbola. Because remember, the bottom of the fraction can't equal 0. So we're going to have some sort of asymptote. So anytime I see one and there's a pronumeral in the denominator, I'm expecting some sort of hyperbolic shape. Now, if those powers are both 1, then I know it's my basic hyperbola. Circles. There's our basic one. X squared plus y squared is the radius squared. And in this case, both of the powers are 2 now, but the coefficients are the same. So you could have 2x squared plus 2y squared equals something. If I had 2x squared plus 3y squared, I wouldn't have a circle. That would be an ellipse. And if it was x squared minus y squared, that also is not a circle. That actually turns out to be a hyperbola. But it's a hyperbola which has been rotated 45 degrees. We won't see too many of those. Extension 2, we look at those. But anyway. Exponentials. There's our basic one. Y-intercept of 1. Because you'll notice x is in the power, and that's how we recognise the exponential. Called an exponential because another name for an index or a power is exponent. And there it is. Y equals a to the power of x. And you go, oh, look, there's a pronumeral in the power. I must have an exponential. That is, of course, if the base is bigger than 1. If the base was less than 1, it would go the other way. Roots. Here we go. The semicircle, we talked a bit about that yesterday. And there it is. Y equals the square root of r squared minus x squared. The other common one we see is that one, half of the parabola, y equals the square root of x. All right. But if you didn't know, square both sides. So if you see the square root sign, that's what's causing you the problem. I don't know what it looks like. Square both sides. So if I was to square both sides, y squared is r squared minus x squared, I could rearrange that and go, oh, it's a circle. But because it's the positive square root, it's the top half of the circle. With the parabola, I go, oh, y equals square root of x. Yeah, not sure. Square both sides. Oh, y squared equals x. It's a parabola. But again, positive square root, top half of the parabola. So, positive square root, top half, negative square root, bottom half. All right, let's have a bit of a playtime. 2G.